Welcome to Linear Algebra, Lecture 1. In this lecture, Professor Michael introduces the geometry of linear equations, the foundation of everything in this course. We will look at the same system of equations in three different ways: the row picture, the column picture, and the matrix form. The fundamental problem of linear algebra is to solve a system of linear equations. Ax equals b. A is the matrix of coefficients. X is the vector of unknowns. And b is the right-hand side vector. We will look at this problem in three ways. First, the row picture, one equation at a time, giving lines or planes. Second, the column picture, the most important view, asking what linear combination of columns produces b. Third, the matrix form, compact algebraic notation. We start with equal numbers of equations and unknowns. The normal, nice case. Let's take our first example. Two equations, two unknowns, 2x minus y equals 0, and negative x plus 2y equals 3. The coefficient matrix A has two rows and two columns. 2 and negative 1 in the first row. Negative 1 and 2 in the second row. The unknown vector x has components x and y. The right-hand side b is 0 and 3. So our system is Ax equals b, where A is a 2 by 2 matrix. Each row of A gives one equation. Each column holds the coefficients of one unknown. Now let's look at the row picture. We take one equation at a time and plot all the points x, y that satisfy it. Each linear equation gives a straight line. The first equation, 2x minus y equals 0, passes through the origin when x is 1, y is 2. The second equation, negative x plus 2y equals 3, does not pass through the origin when y is 0, x is negative 3. When x is negative 1, y is 1. These two lines must intersect somewhere, and that intersection is the solution. Looking at the picture, the lines cross at x equals 1, y equals 2. Let's verify. 2 times 1 minus 2 is 0. Correct. Negative 1 plus 2 times 2 is 3. Correct. The solution is x equals 1, y equals 2. Now the column picture. This is the key idea of the whole course. Instead of looking at one equation at a time, we look at one column at a time. The equation x times column 1 plus y times column 2 equals b asks, what linear combination of the two columns gives b? Column 1 is the vector 2, negative 1. Column 2 is the vector negative 1, 2. We already know the answer. X equals 1 and y equals 2. Let's draw it. Start with 1 times column 1, the vector 2, negative 1. Then add on 2 times column 2, 2 copies of the vector negative 1, 2. The tip lands exactly at b, which is 0, 3. 1 times column 1 plus 2 times column 2 equals b. This operation, multiplying columns by scalars and adding, is called a linear combination. It is the single most important operation in all of linear algebra. Now let's move to 3 equations and 3 unknowns. Our system is 2x minus y equals 0, negative x plus 2y minus z equals negative 1, and negative 3y plus 4z equals 4. The 3 by 3 coefficient matrix A has the numbers from those equations. The unknown vector x has 3 components x, y, z. The right-hand side b is 0, negative 1, 4. This is a 3 by 3 system. Ax equals b. In 3 dimensions, the row picture changes dramatically. Each linear equation no longer gives a line. It gives a plane. Equation 1 gives plane 1. Equation 2 gives plane 2. Equation 3 gives plane 3. Two planes that are not parallel meet in a line. Then that line meets the third plane in a single point. That point is the solution. For our example, the three planes meet at x equals 0, y equals 0, z equals 1. However, you can see that the row picture becomes hard to visualize in 3 dimensions, and nearly impossible in 4 or more. That is why Professor Michael prefers the column picture. Now the column picture for the 3 by 3 system. We write the left side as x times column 1 plus y times column 2 plus z times column 3. And set this equal to b. Column 1 is 2, negative 1, 0. Column 2 is negative 1, 2, negative 3. Column 3 is 0, negative 1, 4. The right-hand side b is 0, negative 1, 4. Wait, b is exactly the same as column 3. So the answer is immediate. Take x equals 0, y equals 0, z equals 1. 1 times column 3 equals b. Let's verify in each equation. 2 times 0 minus 0 is 0. Correct. Negative 0 plus 2 times 0 minus 1 is negative 1. Correct. Negative 3 times 0 plus 4 times 1 is 4. Correct. The column picture found the solution at a glance. This raises the big question. Can we always solve ax equals b for every right-hand side b? Professor Michael shows us a second right-hand side to demonstrate the power of the column picture. Keep the same matrix A, but change b to 1, 1, negative 3. Look at the columns. If we add column 1 and column 2, 2 plus negative 1 is 1. Negative 1 plus 2 is 1. 0 plus negative 3 is negative 3. That is exactly the new b. So the solution is x equals 1, y equals 1, z equals 0. We just take 1 of column 1 plus 1 of column 2 plus 0 of column 3. Verify in each equation. 2 minus 1 is 1. Correct. Negative 1 plus 2 is 1. Correct. Negative 3 plus 0 is negative 3. Correct. The column picture made this solution transparent. Now for the big conceptual question of this lecture. Can we solve ax equals b for every right-hand side b? In column picture terms, do the linear combinations of the columns fill all of 3-dimensional space? Case yes. If the columns are linearly independent, their combinations cover all of 3D space. The matrix is non-singular or invertible. A solution exists for every b. Case no. If the columns are linearly dependent. For example, if column 3 is just column 1 plus column 2 and lies in the same plane as the other two, then all combinations stay on a 2D plane. Most right-hand sides b are not on that plane, so they're unreachable. The matrix is singular. It has no inverse and determinant 0. This extends to any size. N equations. N unknowns. If the n columns are independent, the matrix is invertible and we can solve for any b. If they are dependent, the matrix is singular. Let's summarize Lecture 1, the geometry of linear equations. First, the row picture. Each equation gives a line in 2D or a plane in 3D, and the solution is their intersection. Second, the column picture. The most important view. Ax equals a linear combination of the columns of A, and we seek the combination that produces B. Third, the matrix form. Ax equals B packages everything compactly. Fourth, the key operation. Linear combination. Multiply each column by a scalar and add them up. Fifth, the crucial distinction. If the columns are linearly independent, the matrix is invertible and Ax equals B has a solution for every b. If the columns are dependent, the matrix is singular and some right-hand sides are unreachable. In the next lecture, Professor Michael introduces elimination, the systematic algorithm to actually solve Ax equals B.